So hello everyone, this is lecture 28 for the mathematical physics. In the last lecture we have done the Euler's-Cauchy form and we find it the solution. It was like something this means if you are having this equation, then by changing the operator you will get something like this equation. Then just substituting the value of a here, then you will get the equation which you already know how to find the solution. Okay, means like in the lambda terms you can find the values, and in the last you will just substitute in place of z, that is log x. Okay, that's how you can find the solution. Now today's lecture we will study about the Wronskian. Now what is Wronskian? So remember I told you about the two solutions and their linear independency. So here is we gonna solve them again, okay, using Wronskian. So if this kind of equation you have, this is a homogeneous equation of second order. Now there is this kind of initial condition you have, and now you can have these type of solutions, means y1 and y2. Okay, so and these solutions are linearly independent to each other, definitely. Only then you can write this. I already described that what kind of linear independency I mean. Okay, so if one solution you know, then you can find a second solution. That formula you remember, where y1 was given and y2 was u y1. Okay, there was u as the integral capital U. So I will just tell you, just wait for a second. So what is Wronskian again? So if these two solutions are we have, then if y1 and y2 are two solutions of a homogeneous equations, then Wronskian is defined as, then this determinant is called the Wronskian. Here it is y1 y2 and in their derivative y1 dash y2 dash. So this determinant is called the Wronskian. So if we solve this, we will get y1 y2 dash minus y2 y1 dash. So remember this formula, very important. This is called the Wronskian. Now what is the use of this? If Wronskian came out to be non-zero when you solve the determinant, then we will say that y1 and y2 are linearly independent. And if it came out to be 0, then we will say that y1 and y2 are linearly dependent. So directly by solving the determinant of Wronskian, you can find the linear independency or dependency of y1 and y2. Now let's see an example. This is our equation y double dash plus omega, or w you can say, w square y equal to 0. So if y1 equal to cos omega x, y2 equal to sin omega x. Okay, so these are the solutions. So we will put it in the Wronskian determinant. So it will be cos omega x here, sin omega x here. So differentiation of this will be minus sin omega x omega, cos omega x omega. So solving this determinant, we are getting omega, that is not equal to 0. So we will say that y1 and y2 are linearly independent. So remember this, and it is not just applicable for the 2 into 2 matrix or the two solutions. If you have n solutions, then you can write the matrix like this, Wronskian matrix. f1 f2 to the fn and their respective differentiation up to n minus 1. If it is 2 order, then it will be up to 1. If it will be n order, then it will be n minus 1 for all terms. When you solve this, you will get the linear independency of those solutions. Just remember this determinant, okay, and this formula for the Wronskian. Now let's take an example. Not example, just see that how we can find the different solution y1 y2 by just giving one solution. So using the help of Wronskian, let's see. Let y1 is a known solution, then y2 is u y1. We remember this formula, where this u is capital U dx and its capital U is a upon y1 square exponential minus p dx. And here this p is this p. In the equation you have this p, so just substitute it here. This is the p we have. So this is our solution for y2. Now let's see how Wronskian helps us here. Finding second solution in terms of w. So we need to find the second solution in terms of w. How can we do that? So we know the formula of Wronskian, that is this y1 y2 dash minus y2 y1 dash. Let's differentiate w. So if you differentiate this, then use the product rule in this, so you will get this kind of equation. W dash will be this minus this. Okay, so now you have the solution for the w dash, and w dash is this, and you have already the w. Now let's see this equation. So divide the whole equation by y. Okay, let's see what we will get. Y double dash by y plus px y dash by y equal to minus qx. This is we gonna get. Now see y1 and y2 are the solution of this equation, so we can substitute in place of y, that is y1. So it will be y1 double dash y1 plus px y1 dash divided by y1 equal to minus qx, and y2 is also the solution, so substitute y2 here. y2 double dash y2 plus px y2 dash y2. So these both will be equal because these are equal, can be equated with the help of this minus qx. Now see, take this equation first and then this equation first and multiply with y1 y2 to the whole equation. Then what will you get? For this equation you will get y1 will cancel out, you will get y2 y1 dash, and here you will get y2 y1 dash px and y1 y2 qx. Same from this side, y2 will cancel out, y1 you will get y1 y2 dash, and then it will be y1 y2 dash px equal to this. Now these are equal, so just equate these two equations and rearrange, take the common px and take the terms this side, then you will get this. Now see, this is the equation of Wronskian, w from here. This is w and this is nothing but w dash from here. So we can write this whole term as w dash plus px w. Now see, we are getting very easy equation. Now we can solve this by just separable method. W dash, it will go to the right hand side, then w will came in the denominator and minus px. Now let's take the dw over dx. Dx will go this side and 1 upon w dw will give you log w, and this will be this plus some constant. Now see, from here w will be some exponential of power, means w will be equal to exponential this from this equation, and exponential minus p dx, and exponential c dash will be write as a. Okay, so exponential minus p dx this, and w will be this, means this is our value of w, Wronskian. Now see here, this a exponential minus p dx can be removed by this w, so you will get y2 equal to y1 w over y1 square dx. So now you have the solution of the homogeneous equation, second solution of the homogeneous equation in terms of Wronskian. So remember this formula, very important formula. Okay, let's see an example based on this. X square y double dash minus xy dash plus y equal to 0. So first convert it into the homogeneous form. Divide by x square, you will get this y double dash minus 1 upon x y dash plus y over x square equal to 0. Now see, this is our px minus 1 upon x. So you can write the Wronskian a exponential minus px dx. So you will get log x, and e log x is equal to x. So you will get ax as Wronskian. Now ax over y1 solution is x. So ax over x square dx, x will cancel out, 1 upon x will give you log x. So ax log x will be your solution, second solution. So that's how you can use Wronskian to find the solution. Let's see one more example. This question is asked in the previous year. Y double dash minus 2y dash plus fty equal to 0. Okay, and given is Wronskian at 0 equal to 1. We need to find Wronskian at 2. So if from this equation we can see that this is our fx, sorry px, and here it is in the terms of t, so we will write pt equal to minus 2, and Wronskian is a exponential minus pt dt. This will be minus 2 dt, so it will give you 2t here. Now this is our equation for Wronskian, w equal to ae 2t. So for initial condition using, at t equal to 0 we are getting 1, so we will get a equal to 1. So now w is equal to e exponential 2t. So for 2 it will be exponential 4. So this will be your answer. Now we discussed all the cases. Let's discuss one more thing, that is non-homogeneous linear equation of second order. Means till now we have discussed where Rx was 0 and those equations are homogeneous linear equations. Now we will see the non-linear homogeneous equation, means non-homogeneous linear equations. That is, we are having Rx, something for Rx. So if you are getting something this equation, then the solution will be a general solution, will be sum of homogeneous solution and particular solution. Here this homogeneous solution is nothing but put Rx equal to 0 and solve the equation. Whatever solution you are getting will be your homogeneous solution. So you know how to solve the equation when Rx equal to 0. I already give you enough methods. Now we need to see how to find this particular solution. So where this yx is the solution of this equation, I already told you. Now methods of finding ypx. See, there are infinite numbers of possible functions in the place of Rx. So we will see the particular sum functions which are important, okay, and for the point of view of exams and our applications which you use in the physics. So we'll see only that. So let's see first when Rx equal to in terms of exponential ax. So what will be our solution? So first see, this equation can be written as this. So if we write d over dx as d operator, so this will be our second order differentiation, so it will be d square plus a, this is our single dash, so it will be a d and y will be taken common b. Now this y will taken out, then it will be d square y over dx square dy over dx and y. That's how. So y taken out and rx. Now this is d is operator now. So fd, this function of d, y, this whole thing is called the fd, y equal to rx. Now from here y will be 1 upon fd rx. Here rx is exponential ax. See, you are getting something like this equation. Now solution of this equation will give you particular solution. So if you are getting something this form, then you will just substitute in place of dA and you will get your answer. So this will be your solution. If after placing a in this in place of d, then if you are getting 0 here, f equal to 0, then you will differentiate this f dash d and put it here. So x 1 upon f dash a will be your solution, e exponential ax. Now if this f dash a is coming out again 0, then what will you do? Then you will take the second order derivative and put this like this, x square 1 upon f dash a exponential ax. So that's how you are gonna find the particular solution. It will be more clear with the example. Let's see. If this is your equation, you need to find the particular solution. So fd will be d square plus 6d plus 9. So 1 upon fd multiply this rx, this will be 5 exponential 3x. Now what we need to do, in just a place of d we need to put a. So a is 3 here, substitute 3 3 9 plus 6, 18 and this. So this will be your particular solution. You just need to place in place of d the a, fd equal to fa, whenever you are having something this kind of rx. Let's see one more example. This equation is given. So this is like fd is d square minus 6d plus 9. So 1 upon fd exponential 3x. Now here a is 3, substitute in place of this 3 9 minus 18. So it will cancel out, it will turn out to be 0. 9, then this 9, 18 minus 6 3 18. So it will cancel out, give you 0. So what you will do, you will take the first order derivative of this and place this. So this will be your solution, x into 1 upon 2d minus 6. Now substitute in place of dA. So 6 minus 6, it is coming again coming out 0. So you will take the second order derivative. Okay. So what will be the second order derivative? It will be 2 minus 0. So it will be 2. So it will be x square here. Now this is your particular solution. So that's how you do it. Now let's say in place of e to the power ax, we are having rx equal to x to the power n. Something like this we are having. Then how to find the solution? Then the solution will be 1 upon fd x to the power n will be equal to this. Means you will take the reciprocal of this and solve this inverse and just operate this. Means whatever you are having into the right side of this 1 upon fd, you will operate this whole function on that. Okay. And after operating, it will go to the left side. So let's see one example for this. So what you need to remember here, this d represents the differential operator and 1 upon d represents the integral operator. Whenever you are getting 1 upon d and something on the right side, you will integrate that. Whenever you are getting d and something on the right side, you will differentiate that. So remember this. Let's see an example. This is our equation and this is in the form of x to the power n, because it is here x to the power 0, x to the power 1. So let's see. Write fd will be d square plus 5d plus 4, 3 minus 2x. So we need to operate this on this. So you can't directly operate because we are having the sum of these operators. So you need to take the inverse. And how you can find the inverse of this? So minus 1, it will go upside and minus 1. So you need to solve the binomial expansion for this. So it will be easy if you convert this whole term in the form of 1 plus x to the power n. Okay. So you will take 4 common. It will give you 1 plus d square by 4 plus 5 by 4d. Okay. So you will get something like this. Means whenever you take the 4 common, then take whole term to the above, then it will to the numerator, you will get minus 1 as your index, the power. So you will get something like this, 1 plus 5 by 4d plus d square to the power minus 1. Sorry, there is also 4. Okay. Now see, you need to solve this, and we know the binomial extension of 1 plus x to the power n is nothing but 1 plus nx plus nn minus 1 divided 2x square, and will go on. Okay. But see, we are having in place of x d. So these higher terms, the square terms and the next term, will give when that will operate on this term, so it will just x to the power 1 only, so it will give you 0. So you don't need to put these terms here, you just need these two terms only. So we will use only these two terms. So it is n equal to -1 here, so we'll substitute here 1 minus x, and x is this 5 by 4d plus d square by 4. So we'll get the 1 minus 5 by 4d minus d square by 4 as your solution for this. So I just written it here, 1 upon 4, 1 minus 5 by 4d minus 1 upon 4 d square 3 minus 2x. Now you can operate this whole on this, because take the 3 minus 2x first, multiply with this, it will be 3 minus 2x. Then with this this d will differentiate whole this equation, so it will be 0 minus 2, so it will be minus 2 here with multiplication with 5 by 4. Now d square is nothing but second order derivative of this, so this will be 0 and this will again be 0, so this whole term will be 0, and you are getting only these two terms. Solve this and you have your particular solution. So particular solution for this equation will be this 1 by 8 11 minus 4x. Now see third kind, if you are having sin ax or cos ax in the place of rx, then what will be your solution? So solution will be 1 upon f d square sin ax, means if you are getting something like this form, it can be sin x or cos x, then just replace d with minus a square. So that will be your solution. If minus f minus a square came out to be 0, then take the first order derivative of this form and then place in the place of f d square the minus a square. And this again came out to be 0, then do the same thing, x square then f double dash, until you are getting non-zero number in the denominator. So let's see an example, it will be more easy then. Y double dash plus 4y equal to sin 3x. So fd will be d square plus 4. So 1 upon fd, this function frx sin 3x. So a is 3 and we need to put minus a square in place of d square, so minus a square, so it will be minus 3 square plus 4 sin 3x, it will give you minus 9 plus 4, it will give you minus 5. So minus 1 upon 5 sin 3x. This will be your particular solution. Let's see, we have something cos 2x in the right hand side. So fd will be d square plus 4, it will be cos 2x. So here a is 2, so in place of d square you will write minus a square, so minus 2 to a 4 square, so minus 4 plus 4, it will give you 0. So you need to differentiate it again, so you will get 2d plus 4, 2d only, 2d plus 4 will give you 0, and here will be x. So x sin 2x, and means you will get this 2d plus 4, 2d plus 0, so 1 upon d is 2 and x. So this will be your kind, means from here just use this formula now. This x dot 1 upon f dash d, and just place this. So we differentiate this, it will give us 2d and x here, so x into 1 upon 2d cos 2x. Now this 1 upon d is nothing but integral operator, so we will operate it on the cos 2x. It will give you sin 2x divided by 2. So this will be your particular solution. Now see, let's see one more example. Y double dash plus y dash plus y equal to cos 2x. So fd will be d square plus d plus 1 cos 2x. Now a is 2, in place of d square we will write minus a square, so minus 2 square plus d plus 1, so minus 4 plus 1, it will give you minus 3. Now you need to solve this kind of form. So how you can solve this kind of form? So you will multiply with d plus 3, so you will get d square minus sign in the denominator, d plus 3 on the numerator. Now we can represent means replace the d square with minus a square, as we already know. So a is 2, so minus 2 square minus 9, so it will give you minus 4 minus 9 minus 1 upon 13. Now you can operate this whole term on this, it will be differentiation of cos 2x, then 3 into cos 2x. So cos 2x will give you minus sin 2x 2, so this will be your differentiation, then 3 cos 2x and minus 1 upon 13. So you can directly operate this term, but you can't operate directly this term. So that's how we converted this to this. Or you can use the direct solution if you are getting something like this, 1 upon d plus a cos nx. Means you are having something like this, 1 upon d plus a phi x. This is phi x, 1 upon d plus a. then you can directly write the solution will be exponential minus ax integration of exponential ax phi x dx. So if you use this formula for here, you will get the same solution like this. Okay, try to solve, you will get the same solution. Now let's take one more example. Means if you are having this kind, there is this fourth kind. If Rx is equal to product of something phi x and exponential ax, okay, then what will be the solution? Then solution will be 1 upon fd and operate on this. So this whole term will go to the left hand side, and if it is going to the left hand side means we don't need to operate this on this. So when this go into this side, a will came this side, d plus a. So exponential ax 1 upon f d plus a phi x. So this will be your solution, and you know how to solve this kind of equation. Let's see one example of this. You are having something like this. So fd will be d square minus 4d plus 4 exponential 2x x cube. So if we place in place of d plus 2, then this will go to the left hand side. Exponential 2x 1 upon d plus 2 square minus 4d plus 2 plus 4. At each place d, we write d plus a. Now x cube. So we need to operate this whole term on this. So try to solve this with opening the squares. D square plus 4 plus 4d. Then it will turn out to be d square. All will cancel out. So 1 upon d square x cube. I told you 1 upon d is nothing but integral operator. So this will be 2 times integration of x cube. So it will give you x4 by 4, then x5 by 5 into 4. It will give you x5 by 20 multiply exponential 2x. This will be your solution. Now try to solve this question. I will give solution in the next lecture, and the next lecture will be last lecture for the differential equation. So try to solve this by yourself. Y double dash minus 5 dash 5y dash plus 6y exponential x cos 2x. It will be simple. D square fd will be d square minus 5d plus 6, and you will have this. Then just replace in place of d plus 1, and solve this and operate on this. So try to solve. In the next lecture we will see the solution. Thank you everyone.